Hi everyone! As some of you may know, New York City is among the top 10 most expensive cities in the whole world. That's why we found very interesting to explore a little further the real estate market in the city using machine learning. Our team is composed by Said, Daniela, AJ, and myself, Andrea. We use the dataset of New York City property sales, the one can be found in Kaggle.com. This dataset has a record of every building sold in New York City from 2016 to 2017. It's also composed of 22 columns and approximately 85,000 rows or observations. The contents of this dataset are location, sold price, sold date, address, type, and class of the building's unit sold. The main objective of our project is to find any trend in the housing market in New York City and also to predict the sale value in the future for any property depending on their location. Now Said is going to explain us more about the process overview and the pre-processing of the data.
We use 4 different steps for our project: early pre-processing and cleaning, visualization, pre-processing, and modeling. Early pre-processing and cleaning included cleanup of geolocation data, replacing characters, casting columns to integers, dropping columns that were empty, and creating bins. Second part is visualization, where we did scatter plots and a box plot. Part number 3 is pre-processing, where we used label encoders, one-hot encoder, label binarizer, and a standard scaler to normalize our data. Part number 4 is modeling, where we use 3 different models: linear regression model, random forest model, and deep learning model. Let's get into details of the pre-processing, which was done in 10 different steps for our project. The step number 1 was the geolocation cleaning. We used the US zip code, longitude and latitude data, and a lot of it was we uploaded through a CSV file into our project. Part number 2 is cleaning. Our raw data contained a lot of dashes in the sales price column. We replaced all the dashes with zeros. We converted the land square feet and gross square feet column into integer for graphing. In addition, we dropped easement and apartment number column from our data, because these columns were empty and did not provide any value to our analysis. In the next step, we examined data by using .shape, .dtypes, and describe function to get better understanding of our data. And the step number 4 is mapping, where we map the data using .map function and toDict function. We also created bins for visualization. Step number 5 is stats model API. We use this to get basic understanding of the correlation. We used the correlation on the sales price data to understand the other columns and how much they contribute to our analysis. Step number 7 is label encoder. One of the most important part of pre-processing is encoding. We used a label binarizer, which is a great tool for nominal data. It does hot encoder and label encoder's job in one step. We use label binarizer on 2 columns, which are building class category and borough. For all the other columns, we use label encoder. The next step is the normalization. Standardization and normalization is one of the most important parts of pre-processing. In a standardization, we transformed our values such that the mean of the value is 0 and the standard deviation is 1. We used standard scaler to normalize our data. The step number 9 is training and test data. We split our data into training and test data. And then the last part is the date time. We did date time conversion for sale date by using toDateTime function. and then we will talk about visualization in the next part.
After doing the cleaning, mapping the zip codes into the latitude and longitude, and the borough code into the borough names of Manhattan, the Bronx, Brooklyn, Queens, Staten Island, and creating the bins for the sales prices, now we can visualize our data. In the correlation analysis and the heat map, we can see that the gross square feet and the land square feet are highly correlated, whereas the task class at present and building class at present are not correlated. Those correlations will be included in our model, and we will have to take into consideration the non-correlated variables. For the geo real estate map by district, we can see the geolocation of all the listings in the boroughs. Next, the geo real estate map by prices is representation of the real estate price by geolocation. Based on our expectations of Manhattan being the one with the highest prices, we can see that there are other boroughs that have highest prices as well. There are also many outliers on each of the other boroughs. Our last visualization shows a box plot of housing prices by borough. We want to identify extreme outliers, so we use the 90th percentile to visualize the data. As expected, Manhattan has the highest median prices. The Bronx has the lowest median prices, but it also has a lot of outliers. These outliers will be affecting our model, and we will have to address them.
The first model that we did was a multilinear regression model to predict the sales price. However, this model didn't really perform that well for us. As we can see on the graphs, we chose to use gross square feet to graph it because it is the most important element based on our random forest model that we will explain in the next slide. We can also see that our model presents extreme outliers that causes the bad performance, and you also can see that our mean absolute error is a little over $1 million, which proves that our model is not performing very well.
The next model we will discuss is the random forest model. The random forest model is an ensemble model, and it combines multiple decision trees into one. This model is also our highest performing model. The mean absolute error was 714,000 for this model. This was the best performing model as well. We used an N estimator of 50, and we also, by graphing it, realized that gross square feet, block, year built, building class at time of sale, total units, tax class at present were essential to our current model. This means other aspects can be dropped. Finally, our deep learning model using Keras. We used an activation layer of ReLU as well as linear. We also used the optimizer Atom, and our loss was mean absolute error, keeping it consistent with all of our other models. This model was very interesting due to the fact that we believed it to be the highest performing. However, it came second to the random forest model, as well as beating the linear regression model. The global minimum was around $880,000, which yet again was a surprise. So based off of this, we can say that if we have a model based off of this data, the best model should be the random forest model. All in all, we were very surprised about our deep learning model not being better than our random forest model. However, I believe that we could improve the curious model by feeding more data. However, due to our limited data set, this was the best we could expect from our curious model. We also think that living in New York City has extreme outliers. In addition, even the same area has extreme outliers. Does not matter if you're in Manhattan or the Bronx. There are extreme outliers in each of these areas. So, all in all, we learned how to implement a deep learning model as well as multiple machine learning models. And from all of this, we can make a sound conclusion that a deep learning model isn't always the best model to go with. And sometimes something as simple like a random forest model can outperform both in efficiency as well as accuracy. Thank you so much for this semester.